All right, class. So this is 7.4 properties of special parallelograms. Okay, this is Monday's lesson. And this is the second to last lesson of Unit 7. So whether or not you particularly enjoyed this lesson or this section, or if you didn't, then one win, I guess. But with Unit 7, we're talking about quadrilaterals, of course. And even more specifically, we're talking about special kinds of quadrilaterals. Okay, this is where we get into that flow chart that we should have in our notes. And if we haven't gotten to that flow chart, we do have it online in our Fuji page, so you can access it when you need to. But that's all I'll say about that. And so for today, what we're starting off with is our corollaries and theorems. The first corollary we're going to talk about is the rhombus corollary, and just kind of to abbreviate things first, because we should already have that flow chart available for us, is that we should have 4 congruent sides. That's the main thing we're going to get out of that one. Then we have the rectangle corollary. This is going to be pretty easy. 4 90-degree angles. Or if you want to shorthand it, you can also say 4 right angles like this. That little L with the box is the shorthand for right angles. So if you want to do that, that's perfectly fine. And what we'll find is that square is a combination of both of them. So we both have 4 congruent sides and 4 90-degree angles. That's pretty easy. Then we have our legitimate theorems, our 7.11, 12, and 13. 11 and 12, we probably won't see a whole lot. There might be a couple questions on our exam, but we'll get there when we get there, especially whenever we do our review. But today we actually are going to use both of them. So it is a good idea to kind of talk about what they do. And in essence, the rhombus diagonals theorem just says that diagonals are perpendicular. That's all it says. But then our rhombus opposite angles theorem, that gets a little bit tricky, but the way I describe it is that diagonals will bisect angles. Okay. And then our last bit, theorem 7.13, rectangle diagonals theorem. What this one basically describes is that the diagonals will be congruent. And that is pretty much it. These are our new theorems and corollaries. But again, if you wrote it all down into our table, into our flowchart, you really already have this. And again, if you don't already have this, there is something on Schoology that you can find. It's a PDF of both of them. Just look on the Schoology page and you'll find it. Okay. And as I'm looking at my notes, or rather my my window here for my notes here, I realize I'm actually on the wrong notes. Not necessarily the wrong notes, but the notes that I'm not using for videos. So I'm gonna go ahead and switch to it real quick. But realize that it's all the same. Okay, don't fret. It's all the same. Okay, so I'm just gonna scroll down a little bit to some other notes. So this is what we just talked about. Ooh, it's a little too close. And so now that we have that information, we're gonna look at example 1. In example 1, we are to classify the special quadrilateral and explain our reasoning. Well, the easiest thing to do is to see, well, I have 4, oops, I don't have drawn. I have 4 congruent angles here. And so if I look back at my flowchart, look back at my theorems, my corollaries, and all that jazz, the only thing there's only 2 things that are going to have 4 congruent angles, and that is going to be our rhombus and our square. But you have to really make sure you're going through that checklist. I know that this is a rhombus right now because it doesn't have 90-degree angles. This 70-degree angles, it's going, or this angle rather, is going to stump that. So I know for sure because of this 70-degree angle, I know that this must be a rhombus. A way to think about it for us ninth graders here in geometry, or for our 10th graders who maybe remember this, is that if we think about it as a dichotomy, right? We learned that in biology. Dichotomy basically tells us, oh, is this true, yes or no? If it is true, then you go into this branch. If it's not, then you go to this branch, kind of thing. Okay, so if we kind of think about it like that, where like, for example, mammals, right? All mammals are furry and give birth to like young, and have appendages, so arms and legs and whatnot. But then you get to be more specific, and then we talk about primates and Neanderthals at some point, and then we get humans, right? Those are all that kind of yes, no kind of questionnaire. Like, is this true, yes or no? Is this not true, yes or no? That kind of thing. So this one's gonna be a rhombus because 4 congruent sides. And I would say that's probably the end of your statement there. You probably get in the sentence there. I'm just gonna add in and not perpendicular sides. Okay, remember our perpendicular sides create those right angles, those 90-degree angles. So because we have a 70 degrees, we know for sure this is not perpendicular. Just the way I would explain it. Then extra example 1, we have to explain our reasoning for this shape. You know, be careful, okay? It shows us at first that we have 2 pairs of opposite parallel sides. Well, if I have these 2 pairs of opposite parallel sides, that's what we define to be the parallelogram. Sorry, we are recording this during a drill, so that's what this announcement is.
Chemical shelter in place drill. Thank you. The appropriate safety strategy for this drill is make sure you can accomplish students in your rooms. And in the event something's going on outside, prepare to seal the bottom of the doors.
Okay. Well, I look at my classroom. I have no students because I'm not supposed to have any students, and that's okay. But we have this idea. And as I was saying, we call the 2 sides of opposite parallel angle, or sorry, not angles, sides. And we call that the definition of the parallelogram. And so if we already know this is a parallelogram, we already know a couple things, a couple properties of parallelograms. One being that we have opposite congruent sides. So if you remember from our unit or our lesson 7.1 and 2, we'll know that these sides must be congruent to each other. So if I know that this side in blue is congruent to the opposite side, I know that the opposite side is congruent. But notice that the first one I marked is also congruent with the one on the right, this one. And I know that side I just said is going to be congruent to the other side. So in essence, I've just shown that I have 2 pairs of perpendicular angles, sorry, not angles, perpendicular, parallel sides, parallel sides. And I've just shown that I have all congruent angles. This must be a rhombus. This must be another rhombus for us. And rhombus, well, you know, we can't confirm that it's a square. So because we can't confirm that it's a square, it must only be a rhombus. But we'll just leave it as because for congruent sides. That's what we'll leave it as. And then we'll move on with the time. Okay. Now, example 2 is not actually in our notes. However, I think a lot of us would like to know what some of those answers are. And frankly, you know, I think it's good practice. And what I think you should do as the student is try this one on your own first. Okay, try this one on your own and see how far you can get and determine what you think is the correct answer here. Okay, so if you go back and you were to do this problem, you can ask me about it. I'll have a definitive answer there. But because it wasn't in our notes, I don't have it. I don't have it as an answer, but I can get it for you. But we do have this extra example too, which is actually our real example too. And the way that we're going to do this is, well, we have a couple steps. First thing, of course, we always should draw the figure. In this case, we're going to use our diagram. So we have -2, 3 as our A. Then we have 2, 2 as our B. 1, -2 as our C. And then D is -3, -1. Like so. And so at first glance, well, we can't really determine what it is. It really could be anything, like just not really sure at this point. But something that is nice to know is that our answer choices are rectangle, rhombus, or square. Well, all three of those are parallelograms. Okay, so let's work backwards. If my answer is a parallelogram, then I should follow all the directions of a parallelogram. And what I mean by that is that a parallelogram, of course, the definition says that I have two pairs of parallel sides. Well, if I look at AB, I know AB must be parallel to the opposite side, DC, because that's what the definition of parallelogram means. And so because I know that, then I also know that DA is going to be, not congruent, sorry, is going to be parallel with CB. And this, of course, again, comes from the def of parallelogram. Okay, I'm going to shorthand it. But that four-sided shape is supposed to be a parallelogram. That's the shorthand for it. But we do know some properties of parallelograms. We know prop of parallelogram. That we know that the opposite sides are going to be congruent and the opposite angles are congruent. So not only are AB parallel to each other, but they're also going to be congruent, which in turn, of course, means that they're going to be equal. Same thing with DA and CB. And the last property that we should have is that the measurement of angle A is going to be congruent, or sorry, the angle A is going to be congruent with angle C, and angle D is going to be congruent with angle B. Now, don't forget that because we have congruency, we can also change it to equality. Okay, you just got to switch up the signs a little bit. You got to switch up the notation a little bit, but we can put it into equals. So now I'm officially ready to show this problem. The first thing I'm going to do is I have to determine if I have congruent sides, 90-degree angles, or both. Okay, that's the definition of rhombus, rectangle, and square in that order. So the first thing I'll do is I'm going to determine the length of each side, because I think it's going to be the easiest. But my rhombus test is what I'm going to call it, rhombus test, is to show that AB is equal to DC, which is equal to A, which is equal to CB. That's my rhombus test. I have to show that all four of those lengths are equal to each other. And I'm going to do exactly that. So I'm going to start off with AB. But here, right, I have to use the distance formula, and I know a lot of y'all do not like the distance formula, so we're not going to do it. What we are going to do is Pythagorean theorem. So Pythagorean theorem, I'm going to take those two sides to be my legs. And so if I were to Pythagorean theorem this, I know AB is my C squared, or going to be my C squared. So we'll do AB squared equals 1 squared, oops, plus 4 squared And that's going to equal 17. So we have AB squared equals 17. And to find AB, we know AB to be the square root of 17. You don't have to get any further, just leave it at that. But like I said beforehand, our properties of parallelograms, if we know that AB is equal to the square root of 17, then we also know it's going to be equal to DC. Okay, remember, we're just testing to see if each of them equal to each other. But we know for sure that AB and DC will already be equal to each other. Keep going. We'll find DA. We want DA, which is this blue segment here, or this blue triangle here. Set up the same way, 1 squared plus 4 squared. Don't forget R squared for DA. And this is going to equal 17 again, which leaves us to say that DA squared equals 17. And therefore DA equals the square root of 17, which means that DA is equal to the square root of 17, which is also true for CB. So CB is also equal to the square root of 17. And through a lot of transitive properties, we would say, we know for sure that AB equals DC equals DA equals CB. Therefore, a rhombus test is correct here. Very good, very good. But. Okay. You cannot keep going because we still have a couple options on the board. Just because we show that each side is congruent doesn't mean all the answer choices are eliminated. The only one that we can eliminate is going to be a rectangle. And that's because we did our rhombus test. But we can still possibly have a square. And so because we just done that, again, they're going to exclude that. I would have done this later on because I knew there was a drill today. I would have done it later, but I'm covering another class, so unfortunately I'm here. Now. I would have recorded it later. So that's okay. But we know our rhombus test works. But we still need to figure out if our square works. So for our square, I guess we can call it a square test. Remember the square test, I guess, in a way. The square is just a rectangle and a rhombus smushed together. That's all it is. And so if I've already shown the rhombus way for a square, I need to find the rectangle way. And the only way I'm going to find that rectangle is if I have all 90-degree angles. In other words, because I have a quadrilateral, every single one of our angles has to be compared to each other. So angle A, measurement of angle A must equal the measurement of angle E, which equals the measurement of C, which equals the measurement of angle D. Just like so. So if we can show that these are all equal to each other, we'll be just fine. Well, this is a coordinate plane. The only way to be able to determine that is if they have opposite reciprocal opposite reciprocal slopes. Man, I'm messing up today again. Opposite reciprocal slopes is what's going to tell us if these are 90 degrees angle, 90-degree angle or not. So we'll find these 90 degrees, but the easiest way I find to do this would be if I know the slope of AB. If I know the slope of AB, I also know that slope of AB is the same as slope of DC. So we'll do that. Just because I already have some blue up there, let's find DC. DC is going to be this purple line. My rise is -1 because I'm going downward. My run is 4 because I'm going 4 units to the right. So that's my slopes for those two. But then my slope for DA and CB, well, I'm going to look at this set right here. my run is 4 units up, so I'll leave it. But then my rise is 4 units up, but my run is 1 unit to the right, which is going to equal 4 instead. So because I have negative 1/4 and 4 as my two slopes of the opposite sides, that means I'm going to have opposite reciprocal slopes, which means we are good. Okay. Opposite. Man, I messed that one up. Opposite reciprocal means 90 degrees. Just for us not to forget. So I've just shown the rhombus test. I've just shown the square test. Therefore, the only answer that we can determine this to be is, of course, a square. That's our answer. Because we showed the rhombus test to work, we showed the rectangle test to work, I guess you can call it. And because both of them work at the same time in the same shape, therefore this must be a square. So a bit of a long-winded way to say it. It kind of even looks like a square, even just whenever you draw it. But of course, we can't confirm that until we do. So we had to do it like this. Not too hard. I'm just going to hurry up just a little bit, go a little bit faster. If you have any questions, you, of course, can ask me at an appropriate time. Now, in example 3, in extra example 3, we're going to use the concepts and the theorems of 7.11 and 7.12. 7.11 we're going to need for angle 1, which if we know from example or from theorem 7.11, that the measurement of angle 1 is determined by the diagonals of this rhombus. We know this to be a rhombus because it tells us it's a rhombus. And we can't forget that theorem 7.11 says that rhombuses or rhombi, or the diagonals of rhombi, they intersect each other at 90-degree angles. So the measure of angle 1 is going to be 90 degrees. And that's pretty simple. But we'll find that angles 2, 3, and 4 are going to come from 7.12. The reason being is that if we had diagonals, those diagonals are going to bisect our angles. So, easy way. We know that angle ACD is 61 degrees. And if I know from my ideas of rectangles, or sorry, rhombi and parallelograms, I know if we take out the diagonals, angle A and angle C are congruent to each other. So we know that this whole thing is congruent to each other. But because we have the diagonals, we are bisecting our angles. So if 61 degrees is ACD, then it stands to reason that angle 3 is also 61 degrees. Which of course means that angle 2 must also be 61 degrees. Because remember, the bisector AC is bisecting that angle A. But then for my measure of angle 4, it's actually a little funny. I did it the long way, which you could do the long way, but I don't recommend it. I'm not even going to explain it right now. But I saw a student do this on their paper, and I asked him to explain it to the class. And it was really funny because he said the completely wrong thing. But he had it on his paper, so I was really confused because I thought he had it right, but then I looked back at his answers and it was like, wait, that doesn't make sense at all. But for example, or for angle 4, the best way to do it, you already have 2 of these angle measures, 1 and 3. Notice how we create a triangle here. All right, and if it's kind of hard for us to see, right, this is what a triangle would make whenever we throw our diagonals in there. So if I already have 1 and 3, and I could definitively say what 1 and 3 are, I can figure out what 4 is. I know angle 1 is 90 degrees, which means that the sum of 3 and 4 must equal 90 degrees. So 90 minus 61 degrees is equal to 29 degrees, which therefore means that angle 4 is 90 degrees, or 29 degrees here. Then it tells us that in extra example 3, we're going to find that measure of angle ABC and measure of ACB. Okay, you got to be really careful there. There's definitely an easier one. The measurement of ACB, okay, measurement of ACB is going to be 61 degrees because of that bisected angle. So measurement of angle ACB equals 61 degrees. But angle ABC is going to be a little bit trickier, just a little bit, not too much. Okay. And there's really two ways to go about it. I'll show you, I guess, kind of the longer way, but it's not entirely necessary. But the longer way to explain it is that if I know, again, take out those diagonals. Right? If I know the angle ACB is 61 degrees, that means that the larger angles, the one that's being bisected itself, right? If I were to redraw this, might be a better way to. Without the diagonals, I know it's going to be 61 times 2. So that just means 122. Yes. I know this is 122. I know that the opposite angle is equal. This is also 122. And then I also know that D and B are going to be congruent. Well, I take 360. I subtract 122 minus 122. And I figure out what that is. So if I do some quick math, that's 244, which means that it's going to be, oh, here, let me just do it like this. 360 minus 244, like so, which means that I have 16 remaining after I get 60, and then I have 100 remaining after that. I'm going to have 116 degrees. Okay. After I've determined that, this is not necessarily what our angle is, our angle ABC. But remember, we still are missing that angle D, right? From our diagram, we're missing angle D as well. But we know that they're congruent. So we'll just take 116 and divide it by 2, and we're going to get our answer. So that is 58, which means that the measurement of ABC is going to be equal to 58 degrees. So again, not too hard, not too difficult, but a little bit more work. And that is the longer way, which I think a lot of us are going to resonate with. So I think that's going to be easier for us. But we keep going. And we're looking at example 4 now. And this is where you want to be really careful. Okay, so you are in a building a frame for a window, or you are building a frame for a window. The window must be installed at the opening shown in the diagram. And so what we can glean from this information is that we know the opposite sides are congruent. And remember, our opposite sides converse says that if the opposite sides are congruent, this makes it a parallelogram, which means that the opposite angles are going to be congruent. Like so. I don't expect you to like notate every single thing, but it is at least a little bit important. So it might be nice to show. And so I know for sure that this is a parallelogram. So for sure, parallelogram. And actually, I wouldn't write it right there, right under your question, just so you don't get confused. I'd probably put that up here. Okay, just for your own sake. But just for my sake, I'm just not gonna erase it. Okay. Now the question says the opening must be a rectangle. Given the measurements in the diagram, can you assume that it is? Now remember, you got to go back to our corollary. I think it was corollary 7.3. 7.3 says that the only way to define a rectangle is 4 90-degree angles. If I don't have 4 90-degree angles, then it's not a rectangle. I can't confirm that. I can't say that for sure. And so because I can't say that for sure in this problem, this is not a rectangle. Not a rectangle. You can say a number of things. I would say something like no confirmed angles. From 90-degree angles, maybe at that. Or we can also say not enough information. Oh, I can't spell at all. I'm doing terrible. Enough information. I would say no confirmed 90-degree angles is probably the best way to answer it because it's also showing that you know what it means to be a rectangle, but not enough information is going to be correct as well. But then it follows up with you measure the diagonals of the opening. The diagonals are 54.8 inches and 55.3 inches. What can you conclude about the shape of the opening? Well, the problem here is that we're looking, excuse me, guys. We're looking at our diagonals. Well, if we look at theorem 7.14, or sorry, 7.13, I believe. 7.13 said that if we have congruent diagonals, then we do have a rectangle. But of course, we don't have congruent diagonals because 54.8 is not equal to 55.3. And so what we conclude about this is that it's not a rectangle. Not a rectangle because diagonals are not equal. Oops, that's a poor way to put it. Not equal. I mean, what else we can conclude from this is that we know for sure it's going to be a parallel at the very least. Probably another thing I would add. Definitely a parallelogram. Because we already shown that it's parallelogram. And that is example 4. Again, not too terribly hard. It's just, we got to do a little bit more work, got to think of a little bit more. But this is what we get. So now that we have that, we'll finish off with our examples. In this example, we have a rectangle QRST, which means if we have a rectangle, we're going to have congruent diagonals and 90-degree angles for sure. QS is 5x minus 31, and RT is 2x plus 11. Well, in order for this to be a triangle, we need to figure out the correct x value to say that these are correct diagonals. So we're going to put these diagonals equal to each other because that's what we're supposed to do. So we know QS is supposed to be equal to RT. Put them equal to each other. 5x minus 1 equals 2x plus 11. We'll move all the x's to the left side because I like having a positive x value. And then we'll move all the numbers to the right side. So minus 2x plus 31 on both sides. Make sure you get it right under everything. This is how I do it. If you do it 2 steps, that's perfectly fine. I do it in 1 step. It's easier for me. So I get 3x on the left-hand side, 41 plus 11 plus 41, but 31 is going to be 42. Divide by 3 on both sides. You should get an answer of x equals 14. But you gotta be careful, right? We're not looking for the lengths or the x value, we're looking for the lengths of diagonals. So the length of the diagonal, well, I'm just gonna plug it right back in. I find that RT is gonna be the easier one to solve. So I'll do that one first. 2 times 14 is 28. 28 plus 11 is gonna be 39. And so just to be sure, we're gonna check it again, but with the QS. So 5 times 14 minus 31. 5 times 14 is going to be 70. 70 minus 31 does equal 39. Therefore, diagonals equal 39. I guess you could technically say units, but it's not all that. At least in this problem. Other problems, yes, for sure. This one, not so much. And this is pretty much the same problem, but you gotta make sure you're drawing the picture. Okay, it says rectangle ABCD. Something that's a very important thing to know is that if it tells you a specific order like ABCD, you better follow that order. A, B, C, D. Okay, always how I found it is always counterclockwise or sorry, clockwise. So you go start from the top left and you work your way around back to it. So now this is saying that AC, this line is 7x minus 15. And then it's also saying that BD is 2x plus 25. We're supposed to find the lengths and the diagonals of ABCD. Oh, the lengths of the diagonals, rather. Okay. And we're gonna do the exact same thing. We'll put them equal to each other, find out what x is, and then figure out what their diagonals are. 7x minus 15 equals 2x plus 25. Subtract 22x on both sides, plus 15 on both sides. Cancel, cancel. You get 5x equals 40. Divide by 5, cancel. X equals 8. Right there. Plug it back in. 2 times 8 plus 25. We get 16 plus 25, which gives us 41. Which therefore means that the diagonals equal 41. And that's our lesson. That's all we have to do for today. Tomorrow we'll talk about trapezoids and kites. Won't talk a whole lot necessarily. We'll probably do a little bit more of a review because we do have a quiz on Wednesday and Thursday, but we'll see. We'll see what we'll do. But for right now, this is going to be the end of our video, and I'll check back in tomorrow and see how we're feeling. All right, I'll see y'all later. Bye-bye.